Okay, welcome to the AP Calculus BC. We're going to do lessons 10.11 and 10.14. We're going to find Taylor polynomial approximations of a function and find Taylor and Maclaurin series for a function today. We'll start with identifying with the idea behind a Taylor polynomial. That's what this first video is going to talk about. Then we'll define for you the nth degree Taylor polynomial, show you how to find those, and then we will look for some and work some examples on Taylor polynomials. After that, we'll define a Taylor series and a Maclaurin series, and we will use those and then show you some pretty cool things. One of the things we'll show you is how the alternating harmonic series converges to Ln2 in that. And then we will also develop the Maclaurin series and the power series for functions like 1 over 1 minus x, the geometric series, and for cosine x and sine x and e to the x. So let's take a look and see what we can do. The whole idea behind Taylor polynomial, we're looking for, we can take functions that are difficult to evaluate, that we don't have, can't just use arithmetic and easy calculations to come up with an estimate for a value. And we're looking to write them as polynomials because polynomials are they just depend on operations of multiplication and addition and subtraction. So those are easy to use even with relatively strange numbers. We can calculate by hand. This method was developed before we had calculators and computers, but even the computers use these polynomials, these Taylor polynomials, to calculate things like the value of sine power 5 or cosine 2 power 7. Those values that we can't find perfect or exact values for. Things like e to the 5th power. The calculators use these Taylor polynomials to do that. So what is a Taylor polynomial? It's a polynomial that we use to approximate function values close to a known function value. So we have to know at least one value on our original function that we're trying to approximate with a polynomial before we can use a Taylor polynomial. So if we have some function f of x, and we know that f of a equals b, then we know at least one value, and then we have to be able to calculate the derivatives of the function to write a Taylor polynomial for this. But we don't know what this function is, but let's say we know that f of a equals b, and that we could find derivatives. Depends on how many you can find as to how the degree of the Taylor polynomial you can use to approximate it. We could even write Taylor polynomials for polynomial functions. It would be kind of pointless because they're already polynomials, but we can show you that you would just end up with the polynomial itself if you took enough derivatives of it. But recall that when we did tangent line approximations, we would look for a point on the curve, and we would calculate the derivative there, and then we would find the equation of that line, and we would use that as an approximation, a tangent line approximation for values close to that. That's the same idea behind a Taylor polynomial, except we're going to incorporate more than just the first derivative. So the idea is that if we could create a polynomial function that has the same derivatives as the function we're working with, that the more derivatives we can match to that function, the closer that approximation will be to the actual function. So we can get an even better function by matching a function, not just its first derivative like we did with a tangent line approximation, but if we could find a polynomial that had its first and second derivatives for the same function, then that would make a better approximation than just the first derivative. I can't remember the bells. A tangent line approximation. If we could match the first, second, and third derivatives to the polynomial, or for the polynomial, with the first, second, and third derivatives of the function at that point, then we would have an even better approximation. If we match fourth, fifth, the higher degree of polynomial we get matches more and more derivatives, and so we can make better and better approximations. That's the idea. If we have some arbitrary function, we don't even know what that is, but let's say this is the x value a. And if we know if we know that f of a equals b. If we want a tangent line approximation to that, remember that we find the equation of the tangent line. And that tangent line approximation is y equals, and then we're going to have some constant, the y-intercept. The y-intercept is going to be we'll just say a naught, and then plus some a1 times times x. That's the tangent line approximation. Sorry, some stuff going on in the hallways kind of distracted me there. And that's a first degree polynomial function that we could use to approximate values close to a. Now, you can see by the graph, the farther we get away from a, the worse the approximation is. But what if we could come up with a second degree polynomial that not only matched the first degree, or the first derivative, but also matched the second derivative? Then what we would expect to happen is, let's see if I can find my eraser again. I found it a few minutes ago. There we go. If it matched the first and second degree, or derivative, now it's not only a line, because now if it matches the first and second derivative of A, it's also got to match the concavity. So this is going to go through that point. Red. But it's also going to be concave up like this one is. And so we would expect it to be a better approximator. So what happens when we keep carrying these derivatives out, and we make a third degree Taylor polynomial, would look like y equals a naught, and these are not always the same. These are not all the same a naughts. This is going to depend on the function, all the a sub i's. Maybe different as we make this. Let me not say that. Let me not say that. They may be the same. But we have an a naught plus a sub 1x plus a sub 2x squared. Oops. In a third degree, we have a constant times an x cubed. Now, this one is going to match, when we do this, the third derivative of this polynomial. And what's going to happen is it's going to become an even better approximator to the function than our second degree. Still not matching the function because we don't have a polynomial function, but this one is going to be an even better approximation in that neighborhood close to a. That's the idea behind a Taylor polynomial. The more derivatives we can match, the more the closer we can approximate this function for values close to a. It also just so happens that what tends to happen is these approximations become better for distances farther away from a. Still not the same when we have a finite degree polynomial. But one thing is neat, that if we can find a pattern and we can find a function for those functions that have an infinite number of derivatives, those functions we looked at a few moments ago, like that 1 over 1 minus x, e to the x, cosine x, sine x, those, there are an infinite number of derivatives. So if we could continue to do this and we could match those infinite number of derivatives, we actually find a polynomial expression of infinite degree that is exactly the value, gives us exactly the value of that function centered by whatever this the known point on the graph is. So that's the idea behind Taylor polynomial. We're going to match we're going to match a certain number of derivatives to the function that we start with that we're trying to approximate to our polynomial approximation. We're going to, in general, refer to a first degree Taylor polynomial as p sub 1 of x or t or whatever that value is. Sometimes, some books, some people may refer to it as t sub 1. using Taylor's name. A third degree polynomial, Taylor polynomial, would be p sub 3 of x or t sub 3 of x. Fifth, sixth, whatever, an nth degree Taylor polynomial will denote as p sub n of x. And so whatever the degree is, you can find this, and we're going to show you in the next video how to find the Taylor polynomials to approximate a function value centered around a known point on the graph. This is the idea, basic idea behind Taylor polynomials.